first thing let's do is I'm going to give you a brief tour of this packet. And this, I've been very dissatisfied with the brightness here today. I can make it brighter. Maybe I'll turn the lights way down.
You should be in a musical coming up.
I don't know if I'm going to turn them off, but I'll make it good and dark. Is that good? Let me mess with the brightness again. The problem is if I make it too bright, then when I put my hand in here, sometimes it tries to adjust and it just overdoes it. Is this okay? Too much? Too much? All right. Well, we'll just go with this. So first page is an introduction, and the second couple of pages, this is really what we're focusing on today, adding vectors. You hopefully you're well versed in SOHCAHTOA and inverse tangent mostly. If you know how to do inverse trig functions and trig functions, you should be okay. And Pythagorean theorem, everybody knows that one. The formulas. So on this, you can't see it because it's washed out and I've brightened it, but there are some that are circled in gray. Those are the new ones. And of those new ones, this is sort of the outlier, this thing called the range formula that I think we'll get to today. This is only for projectile motion. It's nice if you want to get a ballpark figure. Let's say you're launching a trebuchet, and you know you're launching it at 30 miles per hour, and you know that the angle is 40 degrees. So you can use this to, like I said, get a ballpark idea of how far it's going to go. So this is the range, the x displacement. It would just be 30 squared times the sine of 80 degrees divided by 9.8. And what's the optimal angle for greatest distance in a vacuum?
45.
45. So what's 2 times 45?
90.
And what's sine of 90?
90.
1. Sine of 90 is 1. So if you shoot at a 45-degree angle, this just becomes v squared over g, which is about, v squared here would be 900 divided by about 10. So it would go about 90. Okay, so this is miles per hour. That won't work. We'd have to convert here. So you'd have to convert miles per hour to meters per second. So divide by about 2.24. So somewhere around, 12, 13 meters per second squared becomes harder. 144 divided by 10, like 14 meters? That doesn't sound like much. I'm making this sound really hard now, but anyway, that's what the range formula does. These other three, does anybody recognize this formula? Some of you have seen this before. Yeah, this is the bonus question from the first test. And how about this one? This was the initial thingy. This was this is the one where on the challenge problem with the person jumping on a trampoline, you needed to derive this basically. And then this one's just kind of common sense. If you look at the acceleration formula and you multiply acceleration times time, what do you get? You get change in velocity. So what this is saying is if you take your initial velocity and you add to that your change in velocity, then you get your new velocity. So these are all just fair game now. You can use any of these whenever you want, and you don't really have to have them. You could derive them, but they're nice to have. And I'll be assuming that you have them, and if you do use these, you can answer the problems with a lot fewer steps than if you didn't. If you were just sticking to the basic ones, you need a bunch of steps. So flipping forward, this is kind of what I'm going to want you to do for projectile problems in the beginning. It looks like a lot of stuff, but it's a little less than it looks like, and it is a lot. So there are 3 different kinds of projectile problems we're going to be doing, and you're going to be doing these with real projectiles. So for example, this says you throw a ball through an open window 20 meters above the point at which you release the ball, 5 meters to the right. So this is what I would call there's the open window. This is what I would call an asymmetric problem. So this ball is going to go up, and it's not going to just stop at its apogee. It's either going to be before its apogee or after its apogee, and in this particular case, it's going to be before the apogee, so it's going to be something like that. It's going into this window at a 27-degree angle. So what you're going to have to find here is, in the y dimension, you're going to have to find v0y and vy, which is the y velocity when it gets to here, and the average y velocity, and all this stuff. In the y dimension, do you know what the acceleration is? You do. Negative 9.8. And then the x dimension is going to be a lot easier because in the x dimension, oh no, sorry, I'm trying to get my pencil to click out some lead. In this dimension, here's v0x. Is there any acceleration in this one? Like as the ball flies through the air, is it accelerating rightward, or is it slowing down rightward, or is it moving at a constant speed? No air resistance for any of these. Constant speed. So in the x dimension, the nice thing is the acceleration is always going to be 0, which means the change in velocity is going to be what? 0. And v0x, vx, and average x velocity, all three of those velocities are the same. So these will be the same. So really in the x dimension, you could just think of this in simple math terms. We've got the rate, and we've got the time, and we have the distance. And all this other stuff is kind of irrelevant. So instead of all these different variables, there's just rate, distance, and time. And rate is velocity, distance is displacement, time is t. And then there's this stuff that's not really in the x dimension or the y, it's a combination. So this angle right here, this would be theta 0, and this would be theta. And then v, if we add up the x velocity and the y velocity like this, the actual velocity is the sum of those two, which we'll get to. That's kind of what we're working on today. So this is an asymmetric problem. This one is what I call a symmetric problem where the range formula works. In a symmetric problem, something takes off and lands at the... That's washed out, isn't it? Something takes off and lands at the same height. So that's a symmetric problem. And then there are going to be some problems like a car driving off a cliff. This is going to be half of a symmetric problem. So those are kind of the three types of problems you're going to deal with, and then in the next unit you're going to have to do these. I'm going to give you a platform and give you a target down here, and you're going to have to put a projectile launcher there and shoot something that's here by aiming straight out. So in order to do that, you're going to have to solve a problem and know how fast the projectile is going to go. We're going to do this where the target's over here, and we're going to put your launcher here so that the projectile comes out at the same height at which it lands. You're going to know what this angle is, and you're going to have to figure out how fast it needs to go to hit the target there. So you're going to be shooting a bunch of different targets and doing some physics to do that. All right, back to the beginning, to the intro. One baseball is dropped at rest, or dropped from rest. So here's a baseball, just dropped. At the same instant, another is thrown horizontally from the same height and follows a curved path, like this. Which baseball hits the ground first? Neither. I was going to say neither. You can do either one. So they hit the ground at the same time. And it's because of Mr. Pennington used to call this the huge idea. I just felt like huge was too big a word, so I changed it to the big idea. And the big idea is the horizontal components and vertical components in 2D motion are independent. So it doesn't matter that this ball has motion in the x direction and the y direction. What's happening in the y direction is the same for both of these balls because they're unaffected by what's happening in the x. There are two kinds of problems. There's a river problem and a projectile motion problem. In past years, we've done a lot of these. We're maybe not going to do any of those, maybe just a little bit. Shh. If you can't, stop giggling. Just go giggle outside. And but we're going to focus on projectile motion. Is it because I said ball? No. Okay, I was just checking. So when a problem has zero acceleration in both the x and y dimensions, it's like this. There's zero x acceleration, zero y. It's called a river problem. And it's called a river problem because the classic example is like a boat trying to cross a river. So it features a boat crossing a river. And when a problem has zero acceleration in the x dimension, like this one, but at the same time it's got negative 9.8 acceleration in the y dimension, then it's more like a bomb problem, except we don't call them that. We call it projectile motion problems. We used to have a question on a test about a plane dropping a bomb. And so this plane's flying at 100 meters per second to the right. It lets go of its package. What's the flight path going to look like of this package? Let's say it hits the ground over here. You're trying to bomb this spot right there with this bomb. Is it going to go like this? No. Yeah. It's curved in what shape? Somebody said this earlier. I missed. It's a parabola. So this is a parabolic trajectory, and this is going to give us a linear trajectory. So going back up here, when a problem it's got zero acceleration this way, but it's got 9.8 acceleration that way, it's called a projectile motion problem. An example of this type of problem is the parabolic arc of a basketball. You could use whatever example you want. Or it could be a bomb being dropped. The first thing we're going to be doing on the next couple of pages is adding vectors, and there are different ways to add vectors, but I'm going to show you the head to tail method, which I think is probably the most basic method of adding vectors. I'm going to show it to you off on the side, then we'll do it some different ways. Say this is a vector, and then I've got this other vector like this. They're kind of tough to add, even if I tell you what the numbers are. Let's just say this one's got a magnitude. I'll make it force. So this is a 5 Newton force vector, and this is a 2 Newton force vector. We can't just do 5 minus 2. Why not? Different angles. Now, if the 2 were like this, then we could do it. Then we could figure out the net force is 3 newtons this way. So the way we add these is by attaching them head to tail. Is this the head or is this the tail? Head. Okay, good. So that makes this the tail. So I can do this 4 different ways. I can take this tail and I can put it on that head. I could take this head, put it on that tail. I could take that tail, put it on that head. I could take that head, put it on that tail. I'm going to do it this way. I'm going to bring this over, keep the orientation the same, and there. I tried to anyway. I don't know if they're exactly the same. So I've got that 2 Newton vector and the 5 Newton vector, and now they're added together. But my next arrow that I draw is going to be like the sum of the two. Can anybody picture? Basically, it's an arrow that substitutes for these. Can you picture what it's going to look like?
Is it going to be start from the tail?
Yeah, it's going to go just like this. So this is the sum of these two vectors. So if you have this one and this one. And right. So now that you look at this, some of you are probably going to have the thought, I can figure some of these things out using law of sines and law of cosines. And that's true. I'm going to show you a simpler way. If you're not comfortable with law of sines and cosines, we're going to be doing it a different way most of the time. So here, Orion, we'll need this. So you don't have to use those. Here's another way of thinking about what I'm doing. I think it's worthwhile. Let's say there's a coconut tree here, and you're a pirate or somebody else is a pirate, and they've given you a map to the treasure or some directions, and the directions say walk 15 paces south from the coconut tree, and then walk 8 paces east from there, and then head north 2 paces like this, and then dig right there. So this is kind of convoluted, but this is like adding three different vectors. It's a displacement vector, another displacement vector, another displacement vector. Instead of that convoluted path, you could have just given one vector which represents the total displacement, and that would be this. So, and then you could just say, stand at the coconut tree, point south, turn 48 degrees to the east of south, and walk 7 paces forward. So you can boil the three different vectors down into one vector. That's what we're going to be doing most of the time today on these pages. But if you wanted to, you could also take this vector and you could break it apart into individual vectors. You could just break it into an x and a y component. These two together are equivalent to that. These three together are equivalent to that. All right. So now some vectors on this. I'm just going to summarize. This says we need to draw vectors representing the x and y motions of the boat and the package. So the boat has a motor that can take it across a still lake at 2 meters per second. So if this were a lake, it would just go straight across 2 meters per second. But the river's current is 4 meters per second. So which way is it actually going to go when it aims straight across? It's going to go this way. And I'm going to draw a series of vectors representing that. So first, this is the x component of the boat's velocity. That comes from its motor. But the boat's also going to be caught up in the current, so that's going to give us a y component, which should be twice as long. So there's the x component, there's the y component. I've added them together head to tail. And can you picture the way the boat's really going? Yeah, so this right here, this is the actual vector sum of those two. That's the way it really goes. So I'll do that again. So from right here, its x velocity is going to be this, its y velocity is going to be this, and the vector sum is that. I'll do this a couple more times, but it gets tedious. There's the x velocity, there's the y velocity, and then there's the actual velocity. So the path that this is traveling in is linear. The path that this travels in is parabolic. So why is this linear?
Because the accelerations are constant.
Yeah, there isn't an acceleration. There's no acceleration, which means this leg of the triangle and this leg of the triangle, they're always the same. So this angle is going to be always the same, and the hypotenuse is always the same. So this is going to be a straight line. But when we do this one, the same kind of thing, one of those two vectors is going to change. Which one's going to change, the x or the y? The y. So go ahead and draw your parabola. I find it's better to just to draw it first. It doesn't have to be beautiful or anything. Just make it a downward curve like that. And I'm going to draw right at the beginning. This is how fast the plane's moving, so that's how fast the package is moving. The package is just released. And at the moment of release, it has this velocity. I'm trying to make this arrow exactly the same length as that arrow. So is there any y velocity at the beginning? No. This is like the ball being dropped up here. You've got a ball being dropped, you've got a ball that's moving sideways. They're both just, there's no y velocity to begin with. Instead of making a chain like this, I'm going to skip a little bit. I'm going to go to here. So at this point, how big should I make the x velocity arrow? I made it this big at the beginning. Should I make it the same size or different? The acceleration in x dimension is 0. Same size. So the x velocity should be exactly that big the whole time. Now, can you picture what the y velocity is going to look like? Hopefully you can, because I'm going to do the y velocity next, but now the direction, the actual velocity is like this. So this is the actual velocity, which means the y velocity is like that. And now I'm going to go a little further, and of these three arrows, v, vy, and vx, which one needs to be exactly the same? Vx. So in the x dimension, there's no acceleration. But because this is getting steeper now, there needs to be a greater y velocity. And then this is v. And I'm going to do one last one. I'm going to do it right down here at the ground, right before it hits. So vx is still pretty short, but now vy is really long. And v is like that. So here there's no vy. I could just write vy equals 0. Here vy is kind of short and downward. Here vy is longer and downward. Here vy is even longer and downward. Why is vy changing? Yeah, because it's doing this. So if the plane had been a helicopter and the ball had just been dropped straight down and I drew all these like x and y vectors all the way down, what would be different? Don't answer that because there are a lot of things. What would the x velocities look like? There wouldn't be any. There would be no x velocity. And so it would kind of, I'll just do it off on the side. It would kind of look like this. So here's everything's 0 in the beginning, and then vy is like that, and then vy is like this, and then vy is like this. And this would be v and vy, because the actual velocity and the y velocity would be the same thing. But there would be no vx. Vx would be 0 the whole time. All right, flip to the next page. Time to add vectors. Like I said, if you're a friend of, if the law of sines and the law of cosines are friends of yours, then you may want to do this kind of thing your own way in the future, but I'm going to show you the basic way of adding vectors. It's going to seem kind of silly and easy in the beginning, but it's going to make more sense when we get to harder ones. So we're going to add vector A and vector B. And one way I can do it is I could just, on this little grid, I can move these so that they're head to tail. So I could do this. I could take vector B and move it over here like this and redraw it. So there's its tail next to this head. And it would be this. So I could measure the distance, the magnitude of this. If this is 3 and this is 4, what's this?
5.
Yeah, it's a 3, 4, 5 triangle. And if you don't remember about 3, 4, 5 triangles, this is a right triangle. So you could do hypotenuse is a square root of 3 squared plus 4 squared, which ends up being 5. The trickier part is, what's this direction, like this angle right here? Is that 45? No. Greater than or less than?
Greater than.
It's going to be greater than, because this leg is 3 and this leg is 4. So anyway, we'll have to figure that out, and for that we do need some trig. So here's the more meticulous way of doing this. We take these vectors A and B, and let's move them down here to a chart. So I'm going to write A and B. And for each of the vectors, we're going to resolve those vectors into an x and a y component. And it's going to seem silly on this one because these are what we call orthogonal vectors that only have one component. So it seems kind of stupid, but it'll seem less stupid in a little while. So if you look at A, is it in the x dimension or is it in the y dimension?
X.
So its x component for its magnitude would be positive 3, and its y component would just be 0. And I'm going to write positive 3. You don't need to write positive 3. Just don't write negative 3. So what's the x component for B? 0. And the y component? Negative 4. So the nice thing about this is you can't really add these vectors. Like I was saying earlier, if you have a box and you have a force of 6 newtons and a force of 12 newtons, then you can add these, 6 minus 12. But if you have a 12 newton force this way and a 6 newton force that way, you can't really do it. So what we're doing is we're taking components that are in the same dimension. Like we've got a 3 newton or a 3 unit vector in the x dimension plus a 0 unit vector in the x dimension, and we get 3. And in the y dimension we get 0 minus 4. So this is the answer. And R stands for resultant. That's the term I'll be using. And then these two vectors that we add up to get the resultant, they're usually called component vectors. And this is a little bit complicated because A and B are component vectors that we're going to add up to get a resultant. But A and B themselves have X and Y component vectors. It's just that some of their components are nothingness. So you take two vectors, you break them into the X and Y parts, you add up the X and Y parts to get the resultant, and then you put the resultant back together over here. So I want to draw a resultant vector with an X component of 3 and a Y component of -4. And you could do it different ways, but I'm going to start from the origin. Do you want me to do the X component first or the Y? Okay, so I'm going to draw a vector going which way, left or right? To the right, and I'm just going to write 3. There are no units here. Now I want to add to that another vector in the Y dimension. So when I draw my other vector, how should it connect to this vector? But tail to tail, head to head, or head to tail?
Start from the head.
Yes, so I can do it two different ways. Let me draw them off to the side. This X component is 3, and the Y component is -4. So I could either take this tail and put it on that head, or this head and put it on that. There's so many different ways I could do it, but since I've got this one drawn, I'm just going to take this tail right here and stick it on right here. I could take this head and stick it on there, but I like to do it this way. Doesn't matter how you do it. This is going to work out nicely though. So, okay. So those are the two X and Y components of the resultant. And the resultant just goes from the open tail to the open head. The components connect head to tail with one another, but the resultant connects tail to tail, head to head. I like to think of it as a nice straight substitution for a couple of crooked vectors. Instead of having this crooked path, we could just have one path going from this tail to that head. So there's the resultant. And to get the magnitude of it, that's just going to be the square root of 3 squared plus 4 squared, which is 5. And now the direction. So I'm going to find this angle, and I'm going to call it theta. I discovered that my other class didn't like the variable theta. They liked alpha better. Problem with alpha, when we get to rotational motion, alpha is the symbol for rotational acceleration. So alpha is out, theta is what everybody uses in basic physics. So we're using theta, whether you like it or not. I'm sorry. So how do I find theta, given this triangle that I've got right here? Trig. So I can relate this leg and this angle together using which trig function? Tangent. So I'm going to write tangent of theta equals, you don't have to go through this process every time, but if the opposite is 4 and the adjacent is 3, then the tangent is 4/3. But that's not what I want. I want theta. So how do I get theta? Inverse tangent. So the inverse tangent of the tangent of theta is theta itself. So if I take the inverse tangent of 4/3, then that gives me theta. On this kind of calculator, I'll show you what it looks like. First of all, make sure that you're in degree mode, not radian mode. A lot of you are probably getting into radians in pre-calc right now, so your calculators might be in radians. Some people have done whole tests in radian mode and had crazy answers at the end. So on this calculator, what I need to do is do everything in order. So I do second tangent, and that gives me the inverse tangent, and then 4 divided by 3, and then enter. And it's 53.1 degrees. So what if I told you the treasure is 53.1 degrees from here? Would that be of any help? relative to something, right? So in pre-calc, there's a certain way people do headings. You can do that if you want. In here, what we're going to do is just pick some kind of a landmark. Like there are two landmarks here. There's what I'm going to call the positive x-axis, is this direction, and then there's the negative y-axis in that direction. Since this angle abuts the positive x direction, I'm going to call this 53.1 degrees below positive x. So you just imagine this direction and then imagine swinging 53.1 degrees below it. 53.1 degrees below positive x. What's another perfectly good way of giving this direction that's not 53.1 degrees? 36, you could say 36.8 degrees. Which direction and from where?
Above negative, or to the right of negative y.
Right of negative y. So that would give this other angle over here. And if you drew your vectors differently, if you drew your 4 first, and then you drew your 3 like this, your triangle might look like this, and then I'm just going to use alpha for that. So if you were trying to find alpha, then you wouldn't be doing the inverse tangent of 4 over 3, you'd be doing the inverse tangent of 3 over 4. And how are those two things related to one another? What's the relationship between the inverse tangent of 4/3 and the inverse tangent of 3/4?
Inversely proportional.
They're complements. They add up to 90. So 3 divided by 4. I heard Lizzie. I know Colby said something. What'd you say?
Inversely proportional.
Inverse. So the 3 and the 4 are inversely proportional to the 4 and the 3, but the angles are complements.
Yeah.
So that angle, that alpha, would be 36.8. All right, time for you to do one. So add vectors E and C. See if you can stay a couple of steps ahead of me, and I'll just catch up here and there. All of the answers to all these are at the bottom. The homework, if you have any homework, is just going to be to do the rest of these. So we'll work through them. E and C are non-orthogonal, meaning they're not just straight up and down. One of them might be. I can't really remember. I could refresh my memory. Neither one. Neither is orthogonal. At least one person's just staring into space. Hopefully you're picturing things out in space. Okay, I'm going to catch up if you want to check and see if you've got the same things I do. What are the x components of E, or x and y components of E? -3, -4, I'm confirming 3 to the left, 4 down, yep. And C, what are the x and y components? 1, -3, yep. Do I hear people retching?
Retching?
Bleh.
Maybe. Don't retch, you're gonna make me
I
retch.
thought I heard some of that. People retch very differently than dogs. Dogs go like that. It's like they have to prime the pump.
Liam Gorniak like that one.
Okay, so R. What's the x component of R? -2. And the y component? -7. Okay, so move on to the next step, unless you've already done it. You got it?
I don't like it, though.
You don't like it?
I don't like it.
What part?
No one says that.
Yeah.
So
So
on, oh, sorry.
people have asked, can you just leave the the answer under the radical, and usually you're going to take that and use it for something. So usually we just convert it to a decimal.
Makes me happier. If only I could do inverse tangent.
Inverse tangent.
Inverse tangent, sorry. When you just say that
you
in
know,
class,
some
because you think
love,
that's what it is.
Yeah, back 50s.
Because you said that one time.
Oh, I see. So your negative two
That's what you mean,
is
like,
just in the x dimension. So it should just go straight over. And negative seven.
When you just say tangent, it's better than straight down. I guess if she doesn't understand.
Yeah, you get a calculator if you need one.
Tangent.
Should definitely practice these calculations if you don't have a calculator. Grab one.
Well, can you grab me one?
Yeah, I can grab you one, bud.
Alan, you're too late. I'm sorry.
Jack.
Get one extra early.
It's a triangle,
Don't just follow me. This is,
These are 72
This is-
one.
this is learning to ride the bike. Some of you aren't even pedaling. You're just waiting for me to push you more.
I'm doing the well.
You don't mind it? I don't mind it.
You need a push? Let me come and look.
It's solar
If I
power.
push you fast enough, you'll just stay out.
Below negative.
So I'm gonna draw mine like other people, like most people haven't drawn yours.
For the, can I do it that way?
Yeah.
Jill, tell me you saw that. Tell me you saw that.
So here's the way most of you haven't done it. I'm gonna do the y component first. I'm gonna go straight down 7. That's not the way most people did it, right? And then I'm going to add on the x component, and I'm going to go straight over 2. And the only reason I'm doing it this way is just to show you can do it that way. It doesn't matter whether you draw this first or this one first, as long as you add them together head to tail. So the resultant is in this direction, and because of the way I've set up my triangle, it looks a little bit more convenient for me to find this angle. Now, if you did it the other way, you'd have your 2 like this, and then you'd add on your 7 like that, and you could find this angle over here. So either of these triangles works. I even saw some people who did it like this. You have, wait, no, you can't. That's forbidden. So if you wanted to put this 7 up top, you would have to do it like this. So you can put the 7 there, and then your resultant would be like that. You could even, how else could I mess this up even more? You could even do the 7 like that, and you could put the 2 here, if you wanted to. And then your vector would be like this. There's so many ways to do this. So the magnitude is just finding the length of this, which is the square root of 7 squared plus 2 squared. And looking down to my answer key, that must be right around 7.3. So 7.3 is the resultant length. And then the direction, I think this is probably the one most people found. So if I'm looking for theta there, I would need to, if this is the angle, then this is the opposite and this is the adjacent. So the inverse tangent of 7 over 2 gives me the angle that I need. And if you're doing this on an iPhone, I'll do it on my phone so it's a little bit different. The order is a little bit different. You do the 7 divided by 2 first, and get that, and then do second and inverse tangent, 74 degrees. So theta is 74 degrees, but just 74 degrees alone will only get you partial credit. You need to tell me 74 degrees in which direction from where. You can either do the heading way you do it in pre-calc, or you can say, this is negative x. I'm going to call it below negative x. Below negative x. Or you can say it's 16 degrees, where from where? Left of negative y. All right. And, not just southwest. So if you just say southwest, that specifically means this angle is what? 45. So if you tell me southwest, that only works if this is 45.
Like with that.
Oh, south, blah, blah, west.
Yeah, what we do.
Yeah, you can do it that way. But if you tell me southwest, I'll assume 45 degrees. Okay, try number 3. So you've got to add 3 different vectors together. And this is where, if you were trying to use other methods, it'd be a little bit harder. So this is where this method is really nice. All I'm going to do is set up my table. I think we're having an eclipse.
Like in the room?
Yeah, that's what it feels like.
Yeah. Like an eclipse party?
No, just an eclipse without the party.
Oh, just like a sad eclipse.
Sad eclipse.
What?
I don't know this guy.
So do number 3.
Wait, you said what?
It says, we're building on it. That's what I thought. We just didn't.
What? It was Liam Gorniak. Alright.
I got all the answers set.
Why is he on his computer? This is not computer time.
Yo, Nat, tell me you're
He's
here.
clearly hiding. Wow.
I'm really
Is that ChatGPT?
Listen, this. Tell me you're here.
I'm also attempting to turn it out. It's 2 here, 4 there.
The resultant compiler. Wait, you mean magnitude?
You go over 4.
I don't know.
Two red hot.
Right?
I'm sorry.
But if you add them together, what's the overall magnitude of the result?
You know what to...
I got you ready.
I don't know, but...
It's looking like it's.
Yeah, so
I
when
don't
you're
know, but it
finding the
makes me
vector,
mad.
Yeah, so it's gonna be 4.472135.955.
it's like find the
Tell me if
velocity
you need
of
anything
the
else.
magnitude and
I sound like ChatGPT.
Oh.
Yes.
So you were still black boys.
Okay.
Great. You know, go great.
You're just finding magnitude and direction. So some people who are ahead have asked on 4, 5, and 6, what does it mean, find the resultant vectors? That means, just like if you were supposed to find the velocity of something, you have to find the direction and the magnitude to really define the vector. So magnitude and direction on those. I'm going to catch up a little bit to anybody who has, or so that anybody who's really stuck can follow along. So D is 0 and 5, C is 1 and -3, A is 3 and 0. So when you add up the X components, you get 4. And when you add up the Y components, you get 2. And if I go over 4 and down 2, then the resultant there is the square root of 4 squared plus 2 squared, which is somewhere around 4.5. So that's the magnitude. And then the direction is just going to be the inverse tangent of 2 over 4, which is 74 to, no, 26.5. Actually, it's 26.6. And this angle will be 26.6 below positive x. Does anybody have any questions about number 3?
It's supposed to be
Is that the
above
gap
X.
supposed to be up?
Did I mess up?
Yeah, it's above X.
Oh, yeah. Yep. So it's this -2. Grrr. Thank you. Thank you. Just pretend that didn't happen.
No, I'm gonna pretend it did.
So 26.6 above positive x. At least I got the hypotenuse right. Still 4.5. Thank you. So positive. Did I screw anything else up, or does anybody have any other questions? Okay. Let's see. We're going to do one other thing, and your homework is to finish those 3. Some of you are working on it right now, but let's skip forward a little bit to take care of page 5. And then you really will have very little to do. And this will set us up to start projectile motion problems next class. Number 4, I'm not really sure what I was thinking when I wrote it. I feel like I deleted something, but what you need to do is draw a vector up and to the right. It can be whatever angle you want. Just make sure it's going up and to the right. And label it V0. And this represents the initial velocity of some vector in one of our projectile motion problems. So let's say you shoot a projectile at 8 meters per second. V0 is 8 meters per second. And you're shooting it at a 40-degree angle. So this is a 40-degree angle. That would just be an example. You'll need to be able to calculate how long it's going to stay in the air, how far it's going to travel, all kinds of other stuff. The first thing, though, is I want to resolve this into the x and y components and sketch the components. So can you picture what I'm about to draw? I'm going to draw the x component of this first. There are 2 different ways I can draw it. One's kind of silly, so I'm not going to do that. So basically the x component and the y component added together give me this. All right, here's the x component. So is anybody uncomfortable by the fact that these 2 are touching tail to tail?
Very.
You are?
I'm so uncomfortable.
It's okay. It's all right. It's legal. So in Vermont. What? Maybe not in some states. So now I don't know what you're all thinking. I don't know what you're thinking. What I'm thinking is so let's say you have component vectors and resultant vector. What kind of vectors are allowed to touch head to tail? They're not allowed to touch tail to tail.
No.
Except that's an R.
Anyone's that meet at 90
So
degrees.
let me write resultant and component. Oh, so which of these 2 can touch one another head to tail? These. So these 2 can touch one another tail to tail or head to head. So this is okay, because this is the resultant and this is a component, and they can touch like that. That's fine. Can you picture the initial y velocity? Right here. So those are the ones that touch head to tail. So yeah, breathe a sigh of relief. Nothing illegal is happening here. Not even in like any state. So we've got the x component, the y component. If you add those together, you get the resultant. And I'm going to write theta in here. And this says use trig identities to express the values of v0x and v0y. So the way this is going to usually work is you'll be given v0 and you'll be given the angle, and then you'll have to find v0x and v0y. So for v0x, what trig function relates v0x, theta, and v0? Sine, cosine, or tangent? Which one? Cosine. So this is the adjacent, this is the hypotenuse. So I'm going to write up here cosine of theta equals v0x over v0. Therefore, v0x equals what? Yeah, v0 cosine theta. So that's what I'm going to write here. So if you're given, you need to shoot a projectile at 8 meters per second at a 40-degree angle, you can figure out the x velocity by multiplying that 8 meters per second times the cosine of 40, and that'll give you this x velocity, which will be constant throughout the entire flight. So the y velocity is going to be, you could probably guess it, v0y.
V0 sine theta.
Yeah, so I'm not going to write that yet, but I almost wrote the same thing. Sine of theta. Sine of theta is opposite over hypotenuse, so it's v0y over v0, and therefore v0y equals v0 sine of theta. So v0 sine theta. And now we're going to derive the range formula. The range formula, I think I told you a little bit about it earlier. The range formula, if you have v0 and you have this angle theta, the range formula will tell you what this distance is, what the displacement is. It only works if you're launching from the same height where something's landing, but it's a kind of handy formula to have. So during this flight, the projectile is going to have its y velocity in the beginning and x velocity in the beginning. Which one of those is going to determine how long it stays in the air, the x or y velocity? Y velocity. If it doesn't have any y velocity, what's it going to do? It's not even going to go in the air. If it has a big y velocity, it's going to stay in the air a long time. So what I want to do first is answer this question. The answer is y. But I want to make an equation for time aloft. And I'm going to get out the formulas which are on the previous page, and I'm going to use one that I showed you earlier but we haven't used before.
Can you use the range from?
That's what we're deriving.
Well, yeah.
So you probably could. But the whole point is to pretend we don't have the range formula and show you how to come up with it. So I'm going to use this one. I'm going to use v equals v0 plus at. We not.
Sorry.
And instead of v equals v0 plus at, I'm going to write vy equals v0y plus ay times t, just to be really clear that I'm working in the y dimension. So this is the final y velocity, this is the initial y velocity, this is going to be negative 9.8, and that's t. So in the beginning, let me just draw it again. If this is the initial y velocity, what does the final y velocity look like? They're the same, but opposites. So instead of vy, I'm going to write negative v0y, because this is the negative of v0y. So that gives me negative v0y equals v0y plus ay times t. And now I'm going to subtract v0y from both sides. I get negative 2 v0y. And what is the acceleration in the y dimension? Negative 9.8. I'm just going to call that negative g times t. So t equals what?
Negative 2 VOY divided by G.
By negative g.
Negative regular G.
So the negatives just go away. So it's 2 v0y over g. And that should kind of make sense if you think about it. Let's just say, imagine this is 19.6 meters per second. So after 1 second going up, how fast is this thing going to be going? If you start out at 19.6 going up, after 1 second, how fast are you going to go? 9.8. After one more second, how fast? 0. And then you're going to come down. So it takes you 2 seconds to go up, 2 seconds to come down. Using this formula, it's basically going to give you the same thing. 2 times 19.6 divided by 9.8, it's going to give you 4 seconds. So now I want to get a formula for delta x here. And the nice thing about the x dimension is I can use this new formula, but it becomes really simple in the x dimension, because in the x dimension, what's the acceleration? 0. So this is all gone, and we get delta x equals v0 times t. This is basically distance equals rate times time. That's what that formula becomes. So I'm just going to write that. Delta x equals vx times t.
Care to scooch the paper down?
Sorry, I zoomed too much. Let me actually call this, I'm going to call it v0x. So displacement is v0x, but we've got another name for v0x, or another way to express it. v0x is v0 times cosine theta. That's what we figured out. So v0 times cosine theta. And instead of t for time aloft, we just figured out that the time aloft is 2v0y over g. So I'm going to substitute that, 2v0y over g. Somebody's going to get to be the star of the math show here soon. Now, v0y, we have another expression for that. v0y is v0 cosine theta. So let me write v0 times cosine theta times 2 v0 sine theta over g. And now combine some stuff. Ugh, I swear my pencil lead is not as strong as it used to be. So there's 2 v0s in here, so I can do v0 squared. And then combine this times 2 cosine theta sine theta over g.
Oh my God.
Does this ring a bell for anybody? Sine 2 theta. So this is sine 2 theta. Yeah. So delta x is v0 squared sine 2 theta over g. So that's the range formula. It doesn't come from any mysterious place. It's now it's right there, and we can use it holding our heads up because we didn't just copy it from nowhere. And that's all we're going to do today. So just finish the other, bless you, problems on page 3 if you haven't finished those, and we're done. I only screwed up once. I did the same thing I did in the